In this screencast, we'll introduce numerical errors and apply those to some simple algorithms. The learning objectives are first to explain the difference between accuracy and precision in our error calculations, and second, to calculate the true error or approximate error for numerical approximations to a given solution. When using numerical methods, we are approximating the solution to a mathematical problem, and we're using algorithms to do this. So the key concept here is that we are creating an approximation, and this means that we aren't always right, and we've got some level of error that's included in our solution. As we think about what constitutes error, let's think in terms of two concepts of accuracy and precision. So first, accuracy is going to be how closely a computed or measured value agrees with the true value. And in precision, it's how closely individually computed or measured values agree with each other. And we can see this figure that's taken from our book. If we look left to right and we have increasing accuracy, you can see that for our bullseye, we have a clear movement away from the target, which isn't on the target. And then for increased accuracy, this is on the target. So we see this in both A and B and C away from the target and D on the target. And then for precision, which is going to be not how close you are to the target, but instead of this, it's how closely each value agrees with each other. As we increase in our precision, you can see that our grouping, which is wide in the top row, becomes tighter in the second row, in C and D. And so if we consider our error being a combination of inaccuracy and imprecision, then the most error that we have is going to be in panel A, where we have low precision and low accuracy. So let's turn our attention to how to calculate errors. And we've done this before in a previous problem using the divide and average method with square root. And first off, the most obvious one would be calculating the true error. The true error would be if we know the true value and we've approximated it using some numerical method, some algorithm, and then we simply calculate the difference between the two. Let's use a real-life example to illustrate error. So let's say that you make $350 in a paycheck, and you deposit your paycheck into the bank, and the bank says they only received $250. So that's their recording of your deposit. And so as we look at this, this hurts. So we've got a total error of $100. Now, Mark Zuckerberg, for his weekly paycheck, he deposits $35,000 into the bank, and the bank, still making the same error, they only record $34,900. And so that error is also $100. Now, as we're looking at our true error column, we can see that both of these are $100. But really, as we're looking at this compared to what the input was for each paycheck, that they're actually not equivalent to each other. So this brings up the concept of, instead of just a true error, looking at a true relative error, where we take the true value minus the approximate value, which is the same as the true error, and then we divide this by the true value. And then multiplying by 100 puts this into a percentage. And so for our true relative error, in our paycheck deposit, that ends up being 26%, whereas for Mark Zuckerberg, that error is 0.286%. And we see that even though the absolute value or the true error is the same in both these situations, you and I would call the bank. But I've got a feeling that Mark Zuckerberg probably wouldn't, based on our levels of pay. These two ways of calculating error, the true error and the true relative error, are really helpful for when designing a new algorithm and you have a test solution that you're comparing to. Let's apply these methods of error calculation to numerical differentiation. And so differentiation is something that we all do and have done, where we have a curve, a function f of x, and there's a point on the line where we want to calculate the slope. And we calculate this derivative as a function using the limit as h approaches 0, where we have the function of x plus h minus f of x over h. And so this would be at the point x. And then also where h is equal to a change in x, or a delta x. We can turn this into a numerical method by considering our h, our delta x, as a change in x that is in front of the point x that we're interested in, behind the point, or the h surrounding the point x. And this gives us what's called the forward difference, backward difference, and the center difference methods of numerical differentiation. Looking specifically at the forward difference method, where our h is in front, we're choosing our h being x of I plus 1 minus x of I. And so if we put another point on here, xi plus 1, this being x of I, we're now basing our slope on a point that is in front of us. So the slope between these two will be the function evaluated at I plus 1, and then the function evaluated at xi divided by that interval. The second option is the backward difference method, and this is where we're defining a point xi minus 1, and then we're looking at the difference between the function evaluated at x sub I and the function evaluated at x sub I minus 1, and then calculating the slope between these points. And then a third option, the center difference, is where we're using the function evaluated at the point xi plus 1 minus the function evaluated at xi minus 1, and then dividing that by the interval of xi plus 1 minus xi minus 1. That would be more like drawing a line in between those 2 points. And so hopefully you can already see that the center difference, the slope of the center difference, seems a little closer to our analytical slope that we drew here in blue, better than either the backward difference or the forward difference in this situation. And given a test case for a function that we know, we could evaluate the error that we incur with using the forward difference method, the backward difference method, and the center difference method, and quantify which one of these provides the best approximation. So let's apply this to a problem where we have a function that's 3x squared plus 4x, and we want to evaluate it at x is equal to 3, and then with an increment of 0.5. And ultimately we want to decide which method of numerical differentiation, being forward difference, backward difference, or center difference, is going to give us the best approximation. And let's do this quantitatively based on our true error and our true relative error. So let's first calculate our true value, and by differentiating this, we get that this is 6x plus 4, and then evaluating our slope at x equals 3, we get the answer of 22. So all of our comparisons are going to be to the true value of 22. And to carry out each of these methods of numerical differentiation, we need to define x sub I, which is 3, x of I plus 1, which is 3.5, and then x at I minus 1, which is 2.5. For our forward difference method, we'll be evaluating at x at I plus 1, subtracting the evaluation at xi, and dividing by that interval. And so our approximation at x equals 3 is equal to the function evaluated at 3.5 minus the function evaluated at 3 divided by the interval which is 0.5. And so evaluating our function at 3.5 gives us 50.75. Evaluating the function at 3 gives us 39. And so this is the answer, 23.5. We'll take the absolute value of the true error, and that's equal to 1.5. Now, putting this into the context of a relative error, making this calculation, it's going to be 1.5 divided by the true value, which is 22, and then expressing that as a percentage. And so our relative error is 6.82%. Let's apply the backward difference method. So our approximation at x equals 3, where we evaluate the function at 3 and then subtract it from the function evaluated at 2.5. And so the function at 3 is equal to 39, and then at 2.5 it's 28.75, which gives us a solution of 20.5. And we see that the error itself is 1.5, just like in the forward difference, and so the relative error is also 6.82%. Let's turn our attention to the center difference, where the approximation of the slope at x equals 3 is equal to the evaluation of the function at 3.5 minus the evaluation of the function at 2.5, and then the increment is going to be 2 times 0.5. And pulling in our values from the backward and forward differences, this is 50.75 minus 28.75. And so our approximate value is 22. And we see that this 22, it matches our actual value. So our true error is equal to 0, and our relative error is also equal to 0%. And so we've confirmed numerically that both the forward difference method, which gives us an error of 6.82%, and the backward difference method of 6.82% error are certainly worse than the center difference method, which in this case gives us 0%. And to put this in the context of where we started with this approximation, with our limit definition, is that as the interval goes to 0, this solution should be more accurate. And so we're seeing here that this interval of 1, using the center difference method, is accurate in this situation. If we increase this interval, let's say our delta x was equal to 1 instead of 0.5, this may have gotten worse. Let's turn our attention to a second example where we want to evaluate the error in a Maclaurin series approximation of the exponential e to the x. And we want to do this when x is equal to 0.5. And so in a Maclaurin series, or any infinite series, we have an option of choosing the number of terms to include. So we have our first term, second term, third term, fourth term, and so on to the number n. And so we want to evaluate it just using the first term, using the first and second, first and third, and so forth. This is another situation where we know the answer. So e raised to the 0.5 is equal to 1.648721. There are plenty more decimal places that we could add, but we'll stop here for this purpose. So let's create a table in which we're evaluating the number of terms, the approximate value using those number of terms, the true error, and then the true relative error. So let's deal with only using our first term. Our approximate value is equal to 1. And so that means that our true error will be 1.649 minus 1. and so the error is 0.649. And then placing the 0.649 divided by 1.649, and then multiplying this by 100% gives us the error of 39.3%. Let's make the same calculations where we include both the first term and the second term. So terms 1 and 2 added together, we can see that we get 1 plus x, and so x is equal to 0.5. So our approximate value is 1.5. So even comparing this to our actual value, 1.649, we're getting closer. And our true error in this case is equal to 0.149. Our relative error, which is 0.149 divided by 1.649 times 100, is 9.04%. Okay, so our true error is getting lower and lower in its absolute value and also in its relative value. We'll do this one more time, adding the third term. We get the value 1.625, and so our absolute true error is 0.024, expressed as a percentage is 3.86%. And so filling out the rest of the chart for terms 1 through 5, we see that our approximate value is 1.648, which is really close to our 1.649. So our true error is 0.001, and then our relative true error is 0.06%. So you can see that we're getting closer and closer and closer. Now, this is a situation where we know the answer. And so that's a great opportunity to be using true error and true relative error in absolute terms. But it raises the question, what if we're using an algorithm where we don't know the answer? And so that's where our approximate relative error or iterative approximate relative error are important. So the approximate relative error is going to be where we're approximating the error, and then we have an approximate value. So in this case, if we don't know the true value, this looks a lot like the true relative error calculation. But most of our algorithms, we're going to be using an iterative approximate relative error. And this is where we have a current approximation minus a previous approximation, and we're going to divide that by the current approximation. Let's apply that to this problem where we'll be adding terms. So we did it with just the first term, then we added a second term to our approximation, and our approximate value matriculated. So hopefully we're becoming better and better and better. And so to get our iterative approximate error, there will be no iterative approximate error for our first term because it's our first approximation. But for our second term, it's going to be current approximation minus our previous approximation divided by our current approximation multiplied by 100%. And then we're seeing that the change in approximation is a 33% change. And so then by adding on a third term, it's our current approximation, 1.625, minus our previous approximation, 1.5, divided by our current approximation. And so for this change in our approximation, we get 7.69%. And then continuing down using the same calculation over and over, this reduces to a change of 1.26%, and then finally 0.15%. And we want this to be less than some tolerance that we've set. Then we can stop our algorithm and be confident that we have converged onto the answer that that algorithm is going to give us. All right, so in summary, we've talked about two different types of errors. This idea that we're going to have a true error in which we need to know the true value to be able to calculate that. Expressing this as a percentage called the true relative error. But if we don't know the true value, then we need to use an approximate error, approximate relative error, or an iterative approximate relative error, and apply this using tolerances Tolerances are going to be where we set these a priori. Once we're below this specified tolerance, we can say that our algorithm has converged.